Thank you for coming. This work is from my PhD dissertation, which I finished in 2021. I definitely want to thank Joseph Olson here. That we, as I'll mention later, investigated a particular PBL scheme, which was coupled for the first time with the BEM scheme, and he did a lot of the work, a lot of the knowledge. He had a lot of the background for the coding work, and I was able to use that to then compare to the observation that I had available in New York. So, moving on. In New York City, during the July 2018, we experienced a regional heat wave. This was actually 1 month before the ICUC meeting. And the criteria for a heat wave is temperatures exceeding at least 3 days above 32 degrees. So you can see there in various locations from, I'll get to that. In various locations from out in the Long Island, more rural areas to all the way New Jersey, you can see that these temperatures during the daytime reached that criteria. And there was a campaign going on at the same time. I will not be covering any ozone results, but if you've heard of the least dose campaign, which stands for the Long Island Sound Tropospheric Ozone Study, they are investigating the spatial variability, and you can see here this 200 AQI, which is really high for ozone. And so this in particular data was very interesting to look at from the many instrumentations that we had. A lot of these observations and the results here are taken from this publication here. But I wanted to investigate this with the Urbanized-WRF and see. A lot of this was a combination of both looking at the observations back to WRF, learning from both of them to then analyze our results together. So the Urbanized-WRF configuration here, you can see we use a 12-kilometer NAM as the input boundary conditions, and going into a 9-kilometer grid, 3-kilometer, and then a 1-kilometer for that urban domain. I'm not going to go into the details of every single one of the configurations, but down here you'll see that the BEM Plus at City College, we've been slowly improving and have been adding more to the static data being used in WRF because of the building information that we have available from the city that they release as open data. Here you can see that we use the NLCD 3 urban land classes configuration. And even though there's only 3 urban land classes, we do think variables like building height are as a separate gridded database. And so we build on, there's certain variables in which we change by using gridded data from this open data database. But we build this configuration has been going on for a while, and we wanted, in particular my research group, having apples to apples comparisons as new studies came along. So one of the other focuses here, as I mentioned earlier, is on the comparisons of what if you just switch the different PBL schemes attached to the urban boundary layer. So one of the key summary of the differences between the different PBL schemes that we have is with regards to MYJ, which is a much older PBL scheme. We see if you look at the equations, it only has a local down gradient, and then the local counter gradient, the counter gradient fluxes in Bullock are more local in nature. And similar to the results that you found in the Alpine Valley, we also found that the night times were an issue. And so we wanted to explore the NYNN in particular because this is used by the National Weather Service as in their high resolution weather modeling as their PBL scheme. However, it had never been linked to an urbanized scheme. And so some takeaways, if there's time, I'll look at some of the PBL results, which as you can see here that a lot of the PBL height is determined with the exception of MYJ, a lot of them are determined based on the near surface temperatures and an arbitrary constant. So if you're able to get the temperatures right, then in theory you should be able to get the PBLs correct. So the choice will determine a lot of the results that we're going to see. And so a brief image of, usually in New York City, we see a lot of the buildings, and that is located right here in Manhattan Island. And here the star represents the PBL profilers that we have that will be looking at the results. So you can see the major terrain, again, not too tall, but this, as the sea breeze moves across, you'll see that as I'll be showing, some of the lines kind of group up past the city in this region. You can see that that's because of the terrain that's occurring after the city. So this is where the highest buildings are. If you're a tourist, this is where you're going to be. And so at the City College of New York, we have a wind profiler and a microwave radiometer. And so these are the configurations. We have pretty good resolution to look at, to compare against our WRF results. And one of the first studies I did was simply looking at a summer of the microwave radiometer results. So I'm going to start on the right. And one of the things that we found is over the winter, in the nighttime and in the daytime, we saw that a persistent superadiabatic layer over the city. And when we looked at the observations for our model, for our particular heat wave case, this is for the nighttime. One of the things when we compared it to the model schemes, we found that this new configuration with the MYN was better able to capture the curvature rather than the other models that seem to impose a more classic structure that you would expect. Of course, this being a coastal city, this is why we see such a stark difference from more the classical structure. Not shown, but there are investigations of more further inland. You will see this development, but because New York City is right on that interface, it makes it a very complex and interesting region to look at. And so, a lot of details here. I think I'm going to try to move quickly through these, but Han looked at the different sea breezes, looking at the observations, a lot of hard work looking at very tiny barbs and the temperature profiles. But as you'll see here, the two times that I want you to note is the earliest that you can see from the observations of the first sea breeze location, which is around 7 in the morning. And then you can see that the sea breeze here kind of passed the city at 11. And so when we look at the observations, we can see that there is the flow in the model is actually a little bit slower based on that. But one of the things that we're able to see, especially in the MYN up here, is it's hard to see here, but these convergence zones that I have highlighted in red. And one of the things as you're trying to track these in the model, this breakup of the sea breeze is something that is also that is reproduced. We still have to go in there and see it further. Consistently, Bulak, as mentioned earlier, the temperatures here, there's not enough mixing going up. It's not enough of that heat being mixed in the upper layers aloft. And we found that MYN tends to match that better, which was very, very good to see. Quickly, so one of we looked back at the models and we compared it to the network of stations, which I'll be showing shortly. And we wanted to ask why could these potentially be getting slower. And we use the variable drag coefficient that is using the building height information within the city. And we can see that these biases go negative right in the city region. So they could be overcorrecting. So that could be something that could be improved with further study. So they're small but negative. Here's a win for Bulak, however, kind of going further out of the city. The RMSE at least tends to improve relative to the other ones. But with this, we can see kind of that contrast, but we didn't dig too deep into the rural area. So this is the station of makeup. Now we're going to look at the vertical cross section. And so that is going to be right here along this line here. So you can see that we cut into the city, and then we've also looked into the terrain further out. And so one of the interesting things, so this is, we're able here to track the vertical. We looked at the observations on the surface. We went back and looked at the vertical structure. We tracked the movement of that sea breeze. Here I have circled. This is where Manhattan Island is. These are the two rivers on that side. And then once you're here, this is New Jersey. But you're able to, one of the features, again, that I talked about at the beginning of my results regarding the superadiabatic layer, you're able to see kind of the trouble for Bulak of mixing that region, consistently, whereas in MYN you're starting to get more of that mixing a lot. And so we think that was a good sign. Of course, not perfect, but I think this proves that this could be a good link for future implementation. So now So this one shows kind of more, maybe more of a misses with the modeling, based on the comparison with the observations. This is very busy. I apologize, but I'll try to focus you right here. This is where we were trying to track the nose of the sea breeze front as it was approaching. So this is our observation. So this is trying to put together the information of the horizontal wind speed from the wind lidar, the vertical wind speed from the LiDAR, which is what the colors are here. So orange here would represent an updraft, and then green to blue would be the downdraft. And so we were able to, looking at these bars represent the horizontal wind speed at that vertical level. Here we saw that there was a bit of this nose occurring as the sea breeze front was passing at around 11. So for the MYNN, one of the things that we were tracking, okay, so what is, if around this time we see that passage, either city or past the city, what are the updrafts from the modeling that we see? And so I tried to highlight those with these vertical blue bars here. And so in summary, BULAC is very popular. It was and commonly used. And so we with our observations, we're able to answer the questions: how can we improve this? Where can we look? And with regards to sea breeze fronts, we can see that the comparisons to observations show that the model progression of sea breeze front is slower than expected based on those surface stations. That breakup may be worth looking more into, and could open up better ways of calibrating the drag coefficient formulation based on the best available building. In other words, how can you use the data that you have to all the building information that we have to maybe create a better formulation, and therefore better drag and better winds with respect to the timings. And how these are, one of the things that we could experiment as well with regards to the model is these particular setups have a lack of the horizontal diffusion in the profiles, and so exploring that, does that actually improve it, or turning those features on, and now that we have the profiles to compare it against. So this linkage, this was a new results regarding the linkage between the MY and N, and so hopefully, since I've graduated, the student after me has taken this to air quality work to use this with WRF Chem, where the linkage between the WRF Chem and MYNN was something that was already built in, but this urban component might have a lot of progress in the future. So, thank you.
Thank you. Thank you very much. Thank you very much, David. Some very colorful graphs. Time for one or maybe two quick questions.
So towards the end, or in your summary, you sort of suggest that we should have a sort of a better or more tailored formulation of drag coefficient. If I remember correctly, the one that's used in WRF or in BEP was based on a series of CFD simulations. Do you have any sort of tips or things you think we should be doing in the future to tailor that formulation, maybe for specific cities or other morphological parameters, perhaps?
I think definitely in New York City, we're definitely spoiled with the information that we have, and so this is one of those examples in which you could potentially update what those CFD results might be and see if there's a way to calibrate it that way. But again, it's the information that you have is probably going to determine how much you can actually do to make these improvements. But it's a very good thing to have, anyways, even if if you're just working from the CFD results.
Thank you, David. Thanks again. Well, sadly, I should say, we're coming to